Welcome to The Explainer. Today, we're doing something humans have literally done since the dawn of time. We're looking up. For as long as humanity has existed, we've stared into that dark expanse above us, searching for meaning, for stories, and eventually for the hard scientific truths of the universe. So today, we're going to bridge those two worlds. We're going to connect the deeply human stories of the night sky with the absolutely incredible science of astrophysics. Okay, let's take a quick look at our roadmap for today. We'll start with our stories in the sky, move on to what makes the stars shine, explore the stellar menagerie, meet our cosmic neighbors, and finally, figure out how we actually measure the vast universe. Let's jump right in. All right, Section 1, our stories in the sky, focusing on moon lore and indigenous constellations. We start our journey by just observing. Long before we had space telescopes or spectroscopy, diverse cultures around the globe tracked time and made sense of the heavens using the absolute greatest tool they had, the power of observation and narrative. Now, most of us grow up hearing about the Greek and Roman constellations, right? Like the Great Bear, Ursa Major, but science and observation are deeply tied to culture. For instance, the exact same cluster of stars that make up the Big Dipper are recognized by the Cree, or Innu people, as Mista Musqua. That was a bullying bear that was ultimately defeated by 7 brave birds. And just like Western star charts, these indigenous stories were, and still are, brilliant instruments of astronomical observation, passed down carefully from generation to generation. And it wasn't just the stars. Our ancestors also mapped the moon's phases, giving them names to track the changing seasons. Native American and colonial sources, for example, named the May full moon the flower moon because of the sudden abundance of spring blooms. And sometimes, orbital mechanics give us something incredibly rare, like a blue micromoon. It's a bit of a mouthful, but here's what it means. A second full moon happening in a single calendar month, that's the blue part, right when the moon reaches its apogee, which is its absolute farthest point from Earth in its elliptical orbit. And because it's farther away, it actually appears slightly smaller and dimmer to us. Moving right along to Section 2, what makes a star shine? The engine of the cosmos. We've mapped them out, sure. But what exactly are they doing up there to produce all that brilliant light? So, way back when, people actually thought stars were up there burning, just like giant lumps of coal. But think about it. If our sun was just a massive lump of burning coal, it would have burned out in a few thousand years. Instead, picture a piece of iron glowing white hot in a blacksmith's forge. A star shines because it is incredibly hot, reaching millions of degrees at its core and thousands of degrees at its surface. But where does all that formidable energy actually come from? Well, it all kicks off when young stars form inside these unbelievably massive clouds of interstellar gas and dust, which is mostly just hydrogen. Gravity provides the initial spark. It pulls these vast clouds together, crushing them into a spherical shape. As all this material collapses inward, it heats up dramatically, eventually stripping molecules down into an electrically charged, super hot plasma. And here is where it gets wild. The nuclear fusion process. Once the core hits about 15 million degrees Celsius, hydrogen nuclei start violently colliding. 4 hydrogen atoms fuse together to create one single helium atom. But here's the magic trick. The new helium atom weighs about 0.7% less than the 4 original hydrogen atoms. So where did the mass go? It didn't just vanish. According to Einstein's famous E=mc² equation, that lost mass is converted directly into energy. To put that into perspective, converting just 1 single kilogram of hydrogen into helium releases the same amount of energy as burning 20,000 tons of coal. Just staggering. So, if you were to bake a star, what's the standard recipe? Because they're born from those primordial clouds and fueled by that intense fusion process, stars are overwhelmingly made of gas. Specifically, about 90% hydrogen and slightly less than 10% helium. Everything else, the oxygen, the carbon, the iron, makes up literally less than 1% of the whole shebang. It's basically a cosmic alchemy lab running right there in the core. All right, Section 3, the stellar menagerie, where we classify the cosmos. Now that we know how they shine, we've got to categorize the incredible diversity of stars out there. Astronomers actually use this awesome letter system to sort stars primarily by their temperature and spectral type. O, B, A, F, G, K, and M. O-type stars are the massive, ultra-hot blue ones. As you move down the list, they get cooler. Our very own sun is just chilling right in the middle as a G-type yellow-white dwarf. Down at the far end, we have the M-type stars, which are the absolute coolest, glowing with this deep orange or red hue. Now, you might assume those giant, blazing blue stars are the standard of the universe. No way. It's actually the complete opposite. The dim, slow-burning red dwarfs, those cool M-type stars, make up the vast majority of stars out there. Because they're so small and cool, they just sip their hydrogen fuel incredibly slowly. A massive blue supergiant might burn through everything in just a few million years and explode as a supernova, but a tiny red dwarf, it can quietly glow away for trillions of years. Trillions. But wait, how do we actually know what category a star falls into if we can't physically travel there? We use spectroscopy. When you look at the spectrum of our sun, you'll see these dark vertical bands. Think of them like a cosmic barcode. Different chemical gases absorb light at very specific wavelengths. By analyzing those dark gaps in a star's light, astronomers can read its exact chemical signature, revealing its temperature, its composition, and its exact classification, without ever leaving Earth. Section 4. Meet the cosmic neighbors. Let's ground all this vastness for a moment by visiting the folks living right next door. 100 billion. Just let that sink in for a second. That is the estimated number of stars in our Milky Way galaxy alone. How on earth do astronomers even count that high? Well, they look at the total infrared brightness of our entire galaxy, which is perfect because infrared light cuts right through space dust, and then they simply divide that massive number by the average brightness of a single star in our solar neighborhood. So out of those 100 billion stars, let's look at who's living right on our street. The Alpha Centauri system is our absolute closest neighbor, at about 4.3 light-years away, and it's actually a triple star system containing Proxima Centauri, a red dwarf that's technically the single closest star to us. A bit further down the road is Barnard's star, another red dwarf. And at 8.6 light-years away, we have Sirius, the brilliant dog star, which is actually a binary system and just so happens to be the brightest star in our night sky. Which brings us to our final stop, Section 5, Measuring the Vast Universe. Because we have to address a really massive logistical question. How do human beings measure things that are literally trillions of miles away? We do it using geometry, specifically a triangulation method called parallax. It's basically an ingenious surveyor's trick. Imagine you're looking at a close star against a backdrop of really distant stars. If we measure its position today and then wait 6 months for the Earth to orbit to the exact opposite side of the sun, we can measure its position again. The star will appear to have shifted slightly. By calculating the angle of that shift and using the entire diameter of Earth's orbit as our baseline, we can calculate the exact distance to the star. If that angle is exactly 1 arcsecond, the star is 1 parsec away, which is roughly 3.26 light-years. Okay, so we've got distance figured out. You can see how that surveyor's trick works. But here's a massive question. How do you weigh a star? Figuring out the mass of an object we can never physically touch, scoop up, or put on a scale is for sure one of astronomy's most incredible tricks. It turns out the secret is gravity and teamwork. Remember earlier when I mentioned that Sirius is a binary star system? Well, more than half of all stars are actually binaries. And because these two stars orbit a common center of gravity, we can literally watch them moving around each other. Think of 2 kids balancing on a seesaw. If they want to balance perfectly, the heavier kid has to sit closer to the pivot point, right? By mathematically measuring their orbital periods and their distances from that common center of gravity, astronomers can precisely calculate the individual mass of each star. Man, we have covered some incredible ground today. From the ancient indigenous observers tracking the moose spirit of Mars, to modern astronomers using the precise geometry of a parsec to map out the Milky Way. Our drive to understand the cosmos, whether that's through vibrant storytelling or rigorous mathematics, is completely universal. We are quite literally made of the very same elements forged right there in those stellar cores, which leaves us to wonder, as our instruments get sharper and our perspectives broaden, what new mind-bending stories will we tell when we look up next? Thanks for joining me on The Explainer.